Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. I'm glad to see we still have a reasonably strong number that show up at 9 o'clock on the second day. That's usually a good sign for a good day. As I mentioned yesterday, we had 90 people continuously. At any given time, at least 90 people were watching the live streaming. And I heard we had actually hundreds of people involved. So not everybody was on the same time, but there were many hundreds. I can't remember the number. But anyway, it was actually quite interesting. There was a tweet stream. You people don't tweet a lot. There was only 3 tweets yesterday, but a lot of people watching. Oh, there was not. It's not on the website. It was actually. Oh, you want to tweet? Okay. Well, I don't want to take away from your time here. So we have once again we have. This is one of the sessions where we have 4 presentations, and so they'll be a little bit shorter than the others. But I want to get started, first of all, with Merce Crosas from Harvard. And this is not her title. It's my mistake. It's close. It's an approximation. So now let's see. We have to do something here.
This? Okay. Okay.
Now we just have to get... Oh, actually, I could get it right here, because I think we have you... Is that you?
Yes.
Ah, good. There.
Okay. I'll be talking about a little bit more than just Dataverse and Consilience. First, I'll introduce the data science team at the Institute for Quantitative Social Science at Harvard University that I'm the director of. We just put together a website. It's going to be public at the end of this week to describe all the research tools that we're working on now. Some, as you will see, some of them we've been working on for years, and some are new from the last month. What we do with the data science group at IQSS is that we combine mainly 3 groups. Some are researchers that have a focus on a statistical, quantitative methods, statistics, and analytics. Then we have a software engineering team, professional team that many of the people there I brought actually from working in industry in the past before I went to join this group at Harvard. And then we have also a data curation and stewardship team that helps with data archiving, preserving data, cataloging and understanding data. And we think that all these 3 aspects are essential to build a data science team that could provide research tools for data-driven science. The team is about 20 people, and you see all the different groups, including QA, the statistical analytics, the software development, data curation and archiving, usability and UI, because we also do a lot of usability testing for our tools, and we find that also to be a critical part of our group, and QA. So let's talk about the applications first. And I'm keeping that a little bit shorter because Dennis told me that let's have a short presentation and then have time for discussion. So feel free to ask also any questions now at the end. So 2 of our main research tools or frameworks that we've been building in the last about 6 to 8 years are Zelic and Dataverse, the Dataverse network. Zelic is a framework, an R framework that is an R common interface that allows to access a large number of statistical methods written in R by different contributors. Often the problem with R is that there are a lot of quantitative methods that are hard to use because each one has been contributed from somebody with different documentation, a different interface. So Zelic brings this common interface to all these models, and it makes it easier to use them and to also it makes it easier to understand them because it has a common documentation for all of them. It's used by, thousands or hundreds of thousands of researchers, actually. It's been used for very, very heavily in quantitative social science research, but also we're expanding into biostatistics and other fields. For the Dataverse is also used widely. We have a Dataverse instance at Harvard that is free and open to all researchers in the world. But it provides a data publishing framework. So it allows researchers to go there, deposit the data set, it generates a citation. It's a key part of Dataverse, so that you have a data citation that you can use to reference the data from a publication, from an article, or from a book. And that way the researcher gets, or the data author or provider gets credit for the data. They have a way to be cited and recognized for the data that might have been hard to collect and put together and clean up. And they keep control of the data. They can set the different permissions on how to access the data. We encourage open access to data, but sometimes there is need for restrictions. And the framework helps you to archive it and preserve it. And also you'll see that it links with Zelic to provide analysis. Then just more recently, in the last months, we've been working on a couple of new projects. So one is Solafide, which is a web interface to the Zelic statistical models. And also it integrates with Dataverse so that you can, researchers, not only researchers are well familiar with the statistical models, but any user, even if they don't have a good understanding of the statistics behind, they can be guided in what a statistical model they can use for if they understand the data. This is going to be released in June, so it's now in development, in testing actually. Data tags is also a new application that is a large collaboration with the computer science department at Harvard, the Bergman Center at the law school at Harvard, and the data privacy lab with Latanya Sweeney. She's also as part of IQSS. And it provides also a framework to be able to tag a data set with the level of sensitivity based on if it has if it's health data or student data, based on the degree of how private that data is, it gives a different tag, and that tag is basically an action, a machine actionable. It has a format that it can be carried with the data set. So it's a policy for that data set to be able to understand how to handle it, how to store it, if it needs to be encrypted or double encrypted, and how it can be accessed. So we try to maximize sharing the data or making the part of the data open, but still restricting the parts that have sensitive data. The two other software applications that we're working on are Consilience and RBIL. Consilience is a text analysis application that uses about 100 different clustering methods that are available in the literature, and combines them to be able to give you a way to interactively or assist you to discover new clusterings, new ways of organizing your documents, not based on the existing methods, but based on new clusterings that are in the clustering space. I'll show a little bit more about that. And then we're just starting to work with this RBIL application that helps researchers that are developing R statistical methods to be able to build them and bring them to CKAN, which is the repository for R packages. So if we put them all together, basically the research tools we're building are part of the entire research cycle from the point of developing quantitative methods to analyzing the data, or either for quantitative data sets or for unstructured text, then publishing that data, making sure that the data are cited from journals, from from any published results, be able to share also sensitive data and allow others to explore, reanalyze, or validate the analysis of the data sets published in Dataverse through sola fide. So then let's talk about it in the cloud, and the part of more interest here. So first, we've been working with Dennis and Krista about we're using Azure for Consilience and part for Dataverse and sola fide also. So in the development of Consilience, well, this is part of the user interface that has a clustering space where you can go over that space and browse all the possible clustering solutions for your document set. Right? And again, this is in development and will be released in June for a few researchers to give us feedback and continue building based on that feedback. But how it is set up, or what is the system workflow basically, and then you see how this maps into how it is set up in Azure. Just that we have you upload a document set that could be from 100 to 1,000, 10,000 or at some point we want to extend to millions of documents, so it goes to tens of thousands for now. You run a clustering map, which involves calculating a term document metrics, running about 100 clustering methods, all the ones that exist in the literature. And this part is the part that can be done in parallel. We then project the results from those clustering methods into two-dimensional space, and then from there we calculate the new clustering solutions in the entire space, building a large grid point for the two-dimensional space of all the potential, the useful clustering solutions for those document sets. So there is a paper by Gary King and Justin Grimmer, one of Gary's grad students that now is a professor at Stanford, that explains part of the methodology followed here. So once we run all this, then users can explore the clustering map. They can discover. I mean, this is I want to point out that this tool is different than other text analysis or clustering tools because it doesn't give you just a solution. It actually gives you a space to explore all the possible solutions, and you choose the one that fits better for what you're looking in your documents. And then it allows you to annotate the documents. So it's set up by using multiple nodes in Azure, and we've been testing expanding the part of the distributed computing using an Akka. I mean, part of the application is written in Scala and Java, and the Scala component follows the Akka. I don't know how many people are familiar here, but have some additional information if you follow that link. It's the Akka distributed workers pattern, so that it can just distribute easily, call as many nodes, use as many nodes to run all the clustering methods that need to be run based on when the nodes are ready to do that, are available. It's actually, I have to say, it's been a very nice, experience. And I'm not the developer doing that, but the two lead developers of that project, they didn't have a chance to do the training, but they've been able to catch up very quickly and be able to. They'll be happy to do the training when it is available, but they were able to set that up easily and make it run very well. So that's been a great experience. The other part is Dataverse in the cloud. We've been setting up a Dataverse instance because we want to do two things with that as for now in Azure. One is that we're testing with CDL, with Patricia Cruz, and so the data app integration with Dataverse. And the other part is that we're just setting up an image for the VM depot to be able to provide for an easy way of setting up a Dataverse instance in the cloud. We're doing that for Dataverse 4.0. That's why it's not ready there yet. It's going to be released at the end of June. And it comes with a whole new UI. There are many big changes, and we wanted to make sure that we would provide the latest when we put this in VM Depot. But it has a new faceted search, new data file ingest, well, a lot of enhancements in the data file ingest, and support for more domains in terms of providing rich the metadata for data sets in not only in social science, but in astronomy, which we've been collaborating with the Simplest Astronomy group at Harvard for a while, but also in biomedical science, and we're collaborating with different groups at Harvard Medical School and affiliated hospitals and other groups worldwide to define a common set of metadata for biomedical data sets. So in this case, another part of what it's in the cloud integrated with Dataverse is Solafide, which, as I said before, is the web application and integrates with Z-Leak to be able to run the statistical models that are in the R, originally written in R, through, and applied to data sets in Dataverse. So it integrates the two systems. And let me see if I can run here. This is a very short demo movie about how it works. You have all the variables for a quantitative data set, and you can see all the summary statistics. All this we generate during the ingest or the upload of those quantitative data sets automatically. And then the user that knows more about the data set can decide what are the explanatory variables, or is the dependent variable, and then look at, choose, here are only a few models that now we have available, but we'll have hundreds of models. And once you set up your, what is the subset that you want to analyze, then you can run that model for the X and the dependent variable that you set up, and you get the results here, which you can take and print out. This is in testing in development, but it's what it will integrate the sophisticated, not only linear regression but quite sophisticated statistical models with data sets in Dataverse. So how is all this set up in the cloud? There is a web app that has the main Dataverse business logic and middle layer, web UI and middle layer. In Glassfish, we have a database node, the storage data files, and then the ingest of when it processes the quantitative data sets that are uploaded to Dataverse are processed in R, so it has an R serve to do that. And then when they are analyzed using Solafide and Z-Leak, it uses R Apache. This we haven't yet set up as with distributed nodes, but these two parts, the ingest and the explorer and the analysis, can be done can be expanded with multiple nodes. Our idea is that to provide in VM Depot one image that is just for a quick testing, that it just everything can. I mean, the nice thing about Dataverse and all with Z-Leak and Solafide is just you can run it all in your laptop as a testing installation, and you can quickly set it up there with one VM. But then also you can set it up for a production solution with several nodes and be able to expand to more nodes for the analysis. So just to know how much time I have. But just quickly introduce also data tags. Well, this is not the cloud yet, but we've been working on the development of that. As I said, data tags helps you to share sensitive data by following the legal regulations that need to follow either HIPAA, FERPA, or other. I think there are 2,800 laws on privacy in the United States, but you can group them all in about 30 types of regulations. And we're working with the Data Privacy Lab and with also the Berman Center at the law school and the computer science, the SIS, the School of Engineering at Harvard. So this gives an idea of the different levels of sensitivity of the data that you would apply to a data set, and you apply that based on an interview that has maybe 10 to 15 questions on your data, and this interview is actually mapped to a set of rules that are set up by the lawyers based on the regulations. So for HIPAA, we got it HIPAA certified by setting up here are the rules, and those rules define a set of questions, and from those questions you're asking the questions. When you finish the interview, you get finally a tagging for your data set. That tag lives with your data set and tells you how it needs to be transferred and stored and used afterwards. So that's it, and thank you, everybody. Thank you.
We have time for a quick question if somebody wants to. Well, Bill is getting his slide
I'll just
set
stand
up.
here.
Anybody? Quick question? Yes.
Some of these tools are available? Are some of these tools available for researchers?
Yes, well, we have almost all of our research tools are open source. Consilience, we're still working out how it will be distributed. It just Z-Leak and Dataverse are now available because we've been developing for a while, and they're available to all the researchers. We have a Dataverse repository at Harvard that is open, free to all researchers, but also other institutions are, many institutions around the world that have set up a Dataverse network for their research data. Z-Leak is also downloadable from CKAN and available to all researchers. All the other ones are going to be released during this summer time. So they're going to be available to researchers then. Yes.
And there should, at some point, there will be a version, as Merce said, that will be in the
in June there will be
depot.
in the VM depot. Yes, yes.
I was wondering whether you have any infrastructure sitting behind data tags that when it identifies that you need two-factor authentication or whatever the tags, is there any infrastructure to help the researcher kind of expose the data with those those restrictions? Or is it just a sort of these are the considerations you need to make?
No, it's more than that, because that's why we're integrating it with Dataverse, so that actually once you deposit the data, I mean, it could be integrated with other type of repositories, other infrastructures for holding data, but once you set that tag, it goes into, it's part of the policy of that the Dataverse follows, and how, I mean, the researcher really doesn't need to do anything. After that, it's all handled properly, because it just follows those, the instructions in the tag, basically. So, yes, and we're reviewing this with different groups, with Steve Chung and Salil Vadan and other people in the computer science department at Harvard to see that it actually, it follows all the security levels that need to follow based on the regulations. So it's not complete yet.
How big are the data sets that you have in Dataverse? You said you have 50,000.
Yes. So the data sets, a data set can has the metadata for that describes the data files, and can have as many files as you want. Each file is has a maximum of 2 to 4 gigabytes. The only thing is that now, for example, we have one new data set that has thousands of files and fMRI data, and each file is maybe less than a gigabyte, but altogether is a large data set. One of the next, I didn't talk about all the future projects, but in the website that we're releasing this week, there is some explanation about one of the next things we're looking for is to extend Dataverse to support more easily much larger data sets. So not only as a sum of multiple files, but building an adaptive data storage behind Dataverse to be able to query quickly data sets of we view of petabytes if we get to extend it to that, because we're working with the Connectome group to do that for image nano scale microscope imaging of the brain. So when you put all these together, those are petabytes, and also with the astronomy group, as you know, that have petabytes. Yeah.
Thanks.
Okay. Thanks. Oh. You probably need that.
So let me,
Got it.
he's got his own. Let me introduce
You can
Bill
take it home
Howe
with you.
and let him get started. Bill, as everybody knows, in the Northwest is one of our leading data scientists, and he will tell us about what's going on in the Northwest.
Thanks. So I wanted to talk about some of the activities we're doing at the eScience Institute here, which has recently been re-energized with a grant from the Gordon and Betty Moore Foundation, the Alfred P. Sloan Foundation. Although our activities and the existence of the eScience Institute predates this award, this has really been able to give us the kind of scale that we've been looking for a while. So this is a joint partnership with NYU, Berkeley, and the University of Washington for a 5-year program to create a data science environment. All right. And so just to give you kind of a scope of this, I'm not going to sort of give you a spiel about data science in general and eScience in general, because I think the audience is sort of cohesive enough in this area that we've sort of seen these pitches before. But just to give us a sense, we put out a call for posters for our rollout event, and we had sort of 137 from departments all around campus, and some of the areas such as like political science were actually some of the most interesting posters that we found. So this is really sort of a pervasive need that we all kind of recognized, but it was nice to sort of see it in practice. So this is a pretty substantial groundswell of interest in these topics, and the eScience Institute, in the context of this award, is really trying to be the umbrella organization to manage this. And just to throw these covers up that we've all sort of seen, this is a fairly old slide here, but what I like is, Roger was here yesterday, and of course here at Microsoft, and I use this quote from him: "It's a great time to be a data geek." But the ugly side of this is this other quote that I like to give a lot, which is this, and I'll let you read it for a second. Right, and so this is perhaps the ugly side of data science. And so what we're trying to do is, and I think probably most of the people in the room here are trying to do, is try to take this term data science and some of the technology and techniques and skills around it and really kind of focus it on astronomy and oceanography and social sciences, physical life and social science, as opposed to only the industry needs. That being said, we really see a lot of interplay between the two sides of it, in that industry can invest deeply in information technology that science sometimes can't, so we can borrow tools and techniques. And going the other way, we see there's kind of a culture of statistical rigor coming out of sciences that I think businesses are only just starting to kind of acquire. So there's really the line between them is blurring, and we like to sort of take advantage of that when we can. Okay, so the way we sort of set this up is to sort of establish a virtuous cycle where just new advances in data science methodologies and techniques and technologies really enable new discoveries, and new discoveries kind of spur requirements in the methodology fields. And to mediate this, we have these working groups across these 6 areas. And in this talk, I just want to focus on 3 of them and give you some highlights from education, software tools, and this idea of working spaces and culture, where we have this data science studio we're building up that I'll end on. And the other ones, just so you see them, are, let's see, I have a pointer here somewhere. Oh, no, don't do that. Maybe I don't have a pointer. No, there's no pointer on here. That's why. That's why it doesn't work. Is there? Oh, that's too complicated. Oh, here it is. Oh, it's quite nice. Yeah. Oh, gosh. Yeah. So burn somebody with this. So reproducibility, I'll point out, the connection between reproducibility and the cloud is great, and I have some slides on that, but I'm not going to show them. I'm happy to talk to you offline. We have this kind of meta-analysis of our own success that we bring up as a first-class citizen, and career paths is a big deal too that I can talk to you about offline, about how we're trying to change the kinds of people we attract and try to keep them around focused on science. But okay, so these 3 I want to focus on this talk. So in education, we have kind of a broad portfolio of programs in data science. There's a certificate program that Roger mentioned yesterday very briefly. He's been involved in helping to design through the University of Washington Educational Outreach Group. There's a massively open online course that I ran last spring that I'm going to run again this summer, I hope, that I'll talk about in the next few slides. There's an NSF grant under the IGERT program, if you're familiar with this. This is for Integrative Graduate Education Research and Traineeship, and this is focused on eventually creating a PhD program in big data, but through a stepping stone of a PhD track. We have new computer science courses focused on big data and data science, all sorts of boot camps and workshops. We ran the Azure, or we hosted the Azure 2-day workshop last summer, for example. This is also a CS course, but we're trying to sort of open it up to people from all majors, kind of a different path into computer science topics. Rather than sort of focusing on games and puzzles, we focus on data analysis as a first-class activity, which we think has a capacity to sort of open up to larger cohorts that aren't typically interested in programming and computer science, but would be if we focus on data. We're getting started on a data science master's degree, and I'll end with this. We have this incubator program that we run out of the studio that's less about a formal education, but has kind of a hands-on training flavor. So a few slides about this MOOC. We ran this through the Coursera platform, and the challenge here, and one of the things I was sort of interested in, was seeing that if we could cherry pick topics from introductory classes that are typically separate, statistics, machine learning, databases, and visualization, and combine them together in one course, which is, maybe a bit of a magic trick. You run the risk of sort of being so superficial that nobody actually learns anything, or sort of, having the intersection of prerequisites be so small that there's only about 3 people in the world that would actually benefit from it. And so I'm reasonably happy with the outcome, and the idea was to try to be sort of superficial and yet have deep dives in particular topics that we think are key ideas that everyone needs to learn. This was the syllabus. We sort of focused on, what is data science, given that the term is sort of new and people have different interpretations of it. We talked about databases and MapReduce and NoSQL, all in this kind of under this umbrella of data manipulation at scale, statistics and machine learning, where of course we can't really give a rigorous introduction to the mathematical concepts in the course of a couple of weeks, but what we can do is sort of teach key algorithms that everyone should be familiar with, and key concepts that I tried to pick ones that aren't typically taught in a Statistics 101 course. I didn't want to do a kind of a compressed Statistics 101 because A, I'm not the right guy to teach that, and B, it'd be somewhat boring. Visualization, and then this week we might swap out with other kinds of special topics, but the first time we did it, we did graph analytics, which seemed to be pretty popular. And then we had guest lectures from various companies. So the participation numbers are fairly fun to give, but some of the bigger ones are kind of meaningless, and I'll explain that. So the number of people who registered was this ridiculously large number of 120,000, but the bar to register for a course is essentially 0, right? You log into Coursera and you click one button and that's it, right? There's obviously no money being paid, but there's not even any kind of sign-up process or anything. So this includes people that had no intention of actually going through the course, that were just sort of exploring things, who were going to watch one video and pick what they want to take and so on. So a slightly more realistic number is people who clicked play on at least one video in the first 2 weeks, which is still quite large, but this is still people who are sort of feeling things out. Now we're getting down to the people who actually intend to take the course. 10,000 people actually turned in the first homework. And after that, the attritions I'm reasonably happy with. So 10,000 turned in the first homework, and about 9,000 completed all the homeworks, which is pretty good. This is partially gained by me because the first homework was a bit of a doozy. So we sort of, if people got through that, they had a pretty high likelihood of being able to get through the rest of it. And this overall attrition rate for a MOOC is pretty standard because the bar is so low. So a lot of times when people are sort of trying to bash these MOOCs, they like to point out the fact that other kinds of online courses in the past have had a much better success rate of keeping people around, but never before has the bar been so low to sign up for these. So it's not quite a very convincing argument to show this and argue that the MOOCs aren't being successful. Although I'm definitely not necessarily a MOOC cheerleader. This is wholly an experiment on our part, so we're not totally sure where this whole thing is going. Okay, and then the number of people who passed was about 7,000. Other kinds of numbers I thought were interesting was the discussion forum was a really critical piece of this, right? I mean, the students who were paying attention and were on top of things could answer questions faster than we and the TAs could, and that's really the only reason why this kind of works at this scale, right? Is you do have this kind of crosstalk in the forums, and so there's quite a bit of activity there. And this has a data set actually to do some analysis on. It's something we're looking into now to see sort of if we can detect when people are learning and how people are learning. Okay, so all this is pretty consistent across, quote, hard courses that have some kind of a technical or programming component to them. Just to illustrate the attrition, this is videos watched, right? So a lot of people watched the first one and then it went down, and again, this is pretty standard. This is the same thing with the assignments, which is a little flatter, which is nice, and this is one assignment and 2 assignments with the different parts. And you can see that as the parts kind of get progressively harder, and so there's some drop off in this sort of Twitter sentiment analysis assignment, and same thing with the databases. We had coverage from all over the world. This is actually not a map that I drew or a survey that I did. This is a student who posted on the forum, hey, where are you from? Mark it on the map. And then I stole that to use it in talks because it was sort of nice. So I didn't actually have to do any of this work. But there's some concentration in the US, but it seems to be pretty much all over. This was a little disappointing. So one of the stories about motivating MOOCs is that there's people who don't traditionally have access to higher education materials who are signing up for these things. And some of the evidence coming out, which has been pointed out before, is that it's not clear that that's really who's taking these things. A lot of times it's people that already have degrees who are professionals and working, who are trying to augment their skill sets, as opposed to people who lack access to higher education materials. And that sort of came here too, is that the biggest number here is, we attracted a lot of professional software engineers as opposed to undergrads in developing nations or something.
But don't you believe those people also have a lack of access to the same materials? I mean, it seems like it does fit your criteria.
Possibly, but I think that they're probably doing pretty well, and they're interested in this, in rounding out their skill sets, as opposed to, basically they have a degree and they're successful and they have a job and so on, which sometimes there's a disconnect between the reality and how the advantages of the MOOCs are pitched, which is, we're giving opportunities to people who don't necessarily have the degree or something. Anyway, it's not all bad. This isn't terrible. It's just that it's not quite the same story that you hear from the purveyors of the MOOCs. But this is pretty standard. People have pointed this out before, that a lot of these courses are being taken by professionals. Okay.
I would agree with Chris. I think this is good news.
Oh, okay. Well, good. I'll respin it. This is great news.
Access to it as being someone who fits that category. I didn't sign up for your class, I'm sorry, but being someone who fits that category, I've taken MOOCs for that very reason, because I don't have the ability to get to a university to take a class.
That's probably
It means I do not have availability or access to it. Just because I'm working doesn't mean I don't have availability.
Well, this room is full of people who have been retrained several times.
That's true. Yeah.
Okay, so if I'm a barista, at what category am I going to land in there?
I don't know. There might be.
You don't seem to have something like working stiff.
Well, working. Great.
Everybody's a professional. What is that?
Working professional non-tech is what I tried to be as a bucket to capture that.
Okay, so let's say that there's 1,760 people that are not in tech. Some of those people might be making minimum wage. You don't know.
Yeah. No, absolutely.
You give them an option to say minimum wage employee.
Oh, well, no, there's certain, if we redo the survey, there's lots of ways to improve the survey. That's not the most, that's not the biggest thing I regret about the way I designed the survey, actually. But I would,
I'm just saying,
you
really can't tell who you're serving in terms of, let's say, underrepresented groups or people who are trying to climb the socioeconomic ladder.
Absolutely, and I was honestly a little nervous about doing too much demography in the survey, because I'm not totally sure of the legality of some of those things. It's a little bit fuzzy, because in some sense I'm officially not representing the University of Washington in these capacities, because otherwise we're into FERPA environments. However, it's not totally obvious that there wouldn't be some flack coming back to the University of Washington if we break some rules. But anyway, I would like a much richer data set of who we're helping, and there might be a way around that, but I was being fairly conservative in this case to make sure I wasn't running afoul of anybody, or making anybody feel uncomfortable trying to answer a question and then give me a bunch of flack. At this scale, everything became a problem, right? If someone can complain, you will get emails. But you're right. I think they're probably partnering with somebody who's better at designing these instruments would be smart. This was a sort of whatever, flying the plane as it's being built, or whatever the metaphor is.
You need to quibble with your main point, which is basically half of them are already software engineers.
Yeah.
Right.
Which wasn't necessarily what I expected, I guess, is my only point. Okay, and the other thing about this scale is that you get these great little anecdotes, because if you have 10,000 people, the odds of something awesome happening is pretty high, and they'll send you an email and you feel good. But of course, I get to cherry pick and pick the ones. But this is sort of fun, right? It's somebody that actually ran a company. Turned out he was a UW grad, and I didn't even know that. But at the time, but he was working on the assignments over in his honeymoon, and ended up selling his company and deciding to take a job with one of the companies that gave a guest lecture in my course as a data scientist, and sort of completely changed his career. And there's other things like this. So it's kind of fun to do this, because you do have the impact at this scale. But okay, so I wanted to mention that we're.
My wife's amusement should be my wife's annoyance.
I was wondering if he had paused over the word amusement myself. Like, did he? Was that for my benefit, or was that the reality? So, okay. So, real quick, I want to mention this. So that's one activity that we're happy with, and we're going to keep running this. This is Magda is the lead PI on the grant, and it's a broad partnership, but she's really been the prime mover through this. If you don't know Magda Balzinski, she's a database faculty at the University of Washington. And the idea here is we stole this from Alex, who claims that he stole it from somebody else, but the provenance is unclear. But this idea of pie-shaped people, right? People heard this analogy before, so some of the people don't know what I'm talking about. So this is, if you're a T-shaped person, you have kind of a thin veneer of interdisciplinarity that we all have, and then kind of a deep leg in one area. And a Greek letter pi would have, two deep legs, right? Maybe you're sort of machine learning and biology, which is some bioinformatics people or something like that. And that we see that the creation and support and incentivizing career paths for these pie-shaped people is kind of one part of our mission, right? We want to create these people and reward them when they do this, as opposed to perhaps what the status quo is, that if you're a biologist and you get a little bit too much into computer science, well, now you're neither fish nor fowl, right? You can't get a job in a biology department because you do too much of that programming stuff that we don't like, and you're not going to be a computer scientist because, well, you didn't sort of write enough papers in SIGMOD or something like that. And yet these people are kind of, in some context, driving science forward. And so we're interested in sort of supporting that. So that's the cute analogy here. The reality is, so this is the NSF program. IGERT is a broad program. They do it every year. That particular year that we had the award, they were specifically looking for these data-enabled science engineering, kind of a data science track. So all the proposals that came in were about kind of big data PhD programs of various forms, and ours was one of the ones that was funded. The key tenets here is that we try to have students in domain science and students in methodology sciences working together as a cohort, whereby the last chapter of the thesis of a PhD student in computer science would be about how their techniques were actually applied in domain science and the actual science that came out of it. And the last chapter in the oceanography student's thesis would be about the new tools they developed and the software they developed. And part of this is not just convincing the student to write that chapter, but also convincing the thesis committees to sort of appreciate that work in both directions. And so we want them to sort of sit together, work together, come up with projects that sort of go together, and I won't go into the details here, but I'm happy to talk to you about it offline. And then, actually, cyber infrastructure development, where we're deploying this stuff and actually seeing it used, is kind of another key theme here, not just sort of throw out proof of concept, but actually get real sustainable tools being built. Okay, and we have participating organizations, or the departments across campus are participating in this, astronomy and genome sciences, as well as computer science and statistics, for example. All right, so that's a couple of points about education. In the software case, I'll try to go faster. I think maybe I'm going to run a little long here. We see the data science can be thought of as this three-step workflow, and this isn't our idea. You see this sort of all over the web, is that there's kind of this first step of preparing data, the second step of actually running the model, and the third step of maybe interpreting and communicating the results. And what we hear from people, and we kind of agree, and we heard a little bit of this yesterday from various people, is that this first step is really the hard one, right? This is the 80% of the work, so to speak. And then the joke is that this is the other 80% of the work. But this number two is not really what's keeping people up at night, right? It's not really about selecting the methods. And there's a couple of reasons for this. One is that simple methods actually go a really long way. Going from we have no predictive analysis capability to we have some predictive analysis capability is a big step. Getting 2% improvement by using someone's sophisticated state-of-the-art method is not really the difficult part. Also, simple methods are the ones that actually scale to large data typically, as opposed to the really intricate ones, and so on. The bad news here is that this step, I claim, is getting the least research attention, actually, right? This one's very fun and easy to sort of, easy. It's very fun to come up with new algorithms and get them published, while this is kind of seen as like, oh, well, that's just some stuff you have to go through, some pain. We'll hire a postdoc who will write a bunch of code, and they'll handle all that step, and then we'll get to the cool part, which is the machine learning to, cure cancer. And then similarly, there needs to be a little bit more emphasis on this as well. This is visualization. It can't be a sort of a black box decision, right? You can't just spit out a number and expect stakeholders to make a decision. Dennis is standing up, so I'm definitely running along here. If you're going to sort of build software around this stuff, if you're going to focus on this step one, you have to sort of answer the question of what are the abstractions of data science. And the fact that we're using terms like data jujitsu and data wrangling and data munging, and this is what you see in sort of on the web and so forth, suggests to me that we don't really have any idea what we're talking about, right? This is bad. And so, but the good news is that I think we do sort of know the abstractions of data science. They just haven't always been recognized as such. Some of the candidates are, matrices and linear algebra, relations and relational algebra. Maybe everything is objects and methods like in Java or C#. files and scripts in computational science. I would claim that only the first two are really viable as potential fundamental abstractions to manage data science workflows. And I would also further argue that relations and relational algebra is under-recognized as a fundamental concept here. And so so some of our software here is really trying to jailbreak relational algebra outside of sort of databases and get it used in more of a data science analytic sort of context. And SQL Share you heard mentioned yesterday, we try to simplify databases down to this simple 3-step workflow of upload data and not worry about a schema. You write your queries and then you share the results with people and that's it. And we sort of organize it on a web-based interface and you can write queries and share them and so on. And we've had a lot of uptake in science for this, where previously they never would have used databases. We've got people that don't write any program, code in any language whatsoever, not R, not Python or anything, but they write these sort of 40-line hairy SQL queries that do like interval analysis on, genomic data or whatever. So this is a pretty good sign that maybe there's something, this whole declarative language thing actually has some weight behind it. We see R scripts being translated into SQL queries, and they sort of ostensibly don't get more complicated when you do that. They sort of have the same expressive power, and yet the one on the right scales sort of infinitely, right? We know how to sort of scale this program up. We don't know how to scale the R program up. We being everybody. Stephen Roberts gave a talk yesterday. He takes, Galaxy workflows that have this kind of complicated multi-step kind of thing going on, and they get kind of compressed down to a handful of queries, and so on. We're teaching people SQL in sort of workshops and so on. But, the problem here, and I'll wrap up here, the problem here is that that's just SQL, that's just relational algebra. There's a certain class of analytics tasks that you can't do in SQL, and we're trying to see if we can take what we like about relational algebra and add just enough more richness to capture a lot more of the steps. And so instead of query as a service, we think about this kind of relational analytics as a service. There's a big team, a bunch of students working on this. I'll skip the architecture. We have a little relational database on each node, and it's a big parallel sort of engine. The other weakness of SQL Share perhaps is that it wasn't really focused on sort of hundreds of terabytes, and INRIA is. So the two big things about INRIA are iterative queries. So you can do loops, which means you can express things that converge, right? You can express analytics tasks and clustering tasks and so on. And then it also scales a lot. It scales sort of as well as we know how to do at the state of the art. So fine. So we have this kind of theory of We have this notion of relational algorithmics. We want you to do algorithm design, but you're using relational algebra right there in your program, kind of like LINQ and C#. And this is k-means in our little language, where everything here is relational algebra, but it's expressing k-means. I'll skip this, I guess. This is manually optimizing a program. Here's a simple relational algebra version of it to a increasingly complex one where it gets faster, but there's no hope that the database optimizer is going to magically turn out this program from the original one. So you actually do need to have the programmer kind of working in this space. So it's not just query optimization, it's actually algorithm design, and yet every single line is relational algebra. Okay, and we want query debugging and visual analytics of the running of these things to be kind of a first-class citizen, as opposed to something only DBAs do. We want the actual analysts and the scientists to be doing this stuff, so we have some visualization work in this space. And then let me just wrap up with this. We're conscious of the need for physical proximity, or we believe, our hypothesis that physical proximity between the computer science and statisticians and methodology people and the domain scientists is sort of important. And so we're trying to set up a data science studio here on campus where they can sit and work together and run programs through this. And one of the programs we're running is this incubation program where people submit one-page proposals. There's no money exchange. They get to come and sit elbow to elbow with our staff, our data science staff, and thereby hopefully take sort of a 2-week problem of trying to figure out how to use GitHub and and Hadoop into a kind of a 2-hour problem, because we have expertise right there in the room to do it, and really focus on these short-term, small bet, high payoff kind of projects, as opposed to the big sprawling 2-year let's write an NSF grant together kinds of things. And this seems to be working pretty well. We're running a pilot of this this quarter, and we have projects spanning social sciences. We're here where there's some manifold, in finding these embedded manifolds, but they need to scale this method up. This is some work by Ian Kelly here, right here in the room, who's looking at cell phone call logs and correlating that with events such as bomb blasts. And we're doing a systematic analysis of different kinds of tools for this job, cloud, on the cloud and off the cloud, and so on. So this has been pretty successful. And then if you want to get involved, there's various ways, and you can take the MOOC, you can talk to me about these incubator projects. We'd love to have people come by and either work on either side of the desk, either to come and actually work on their own project or to help other people with their projects. We have a notion of reverse internships where we hope to attract people from industry to come and physically come and hang out with us for a quarter. And also we're pretty committed to coming up with reusable materials around all these programs so that if other people at other institutions want to try these programs out, like run their own incubator, they can borrow from us if that's somehow useful. And I'll stop there since I'm over, I think, by a lot.
So while Gabriel is setting up, we can take a few questions. Yes.
Hi, on Bill. So kind of related in terms of the education piece, I think.
Yeah.
So I think it's fair to say that in academia you don't get promoted for writing software.
Yeah.
Right. So in this data science environment, are you trying to tackle that, or are you actually creating a problem?
No, that's exactly right.
So, yeah,
I didn't talk about it, but there's one of the working groups is career paths, and it's exactly that. You know, one of the observations that we have is that we're producing people with PhDs who are not in some cases who are not necessarily motivated by the traditional academic career path. We lose 100% of these people to industry to a first approximation, right? There's literally no appropriate job for them on campus. So sometimes there's a staff programmer job where you're beholden to some particular investigator in some particular department and you live or die by their interests. But that's not a very competitive, attractive job compared to what they get in the industry, even ignoring salary, which we can't get beat on. And so we're trying to say, what if we came up with this data science studio where they had some autonomy, they had some prestige, they have some control over what they work on, they have probably still can't compete on salary, but we can do a decent salary. And we hope to attract these people back through that and actually give them kind of a career path where they can grow and get promoted in various ways for doing this kind of work. And we'll see if ask me in 5 years whether it worked or not, but we have some early success in that we've had people that have been thinking about what to do next, deciding to come and work with us that are incredibly good. Dan Halperin from the UW-CS, he has a PhD in computer science and got excited about this sort of eScience stuff and came back to work with us. Jake Vanderblas, a PhD in astronomy, who's a machine learning expert, decided to come back to work with us. So we have some success stories already.
Thanks a lot, Bill. This is really terrific stuff, and I'm delighted it's going on here. You had enough good stuff in there to come back again and give a 2-hour talk. All right, so Gabriel has been working on a project that we have been helping with in INRIA for the last 3 years, and he's going to give us a quick update on it.
Right, thank you very much, Dennis. First of all, I'd like to thank you for the nice opportunity to be here. So I greatly appreciate that. It's very exciting. It's a very exciting workshop. So the projects I'm going to talk about are about data-intensive computing on clouds, obviously on Azure clouds, for science applications. So these are projects that have been carried out in the framework of the Microsoft Research INRIA Joint Center, which has a very nice location in Paris, but it's actually not a centralized center. It involves teams for several research centers at INRIA. So INRIA is the main research institute in computer science in France. It has 8 research centers. And in these projects, we have teams involved from 3 centers. So I'm personally in charge of one of the research groups that is called KL Data, focusing on scalable data storage and processing for large-scale distributed infrastructures. So the first project I'm going to talk about is called A-Brain. So it's basically the first cloud-oriented project within this joint INRIA Microsoft Research Center. It was started as part of the Cloud Research Engagement Initiative directed by Dennis, so one of the first French projects in this framework. From the infrastructure level, one of the goals was to assess the potential benefits of the Azure infrastructure for science projects. In this particular project, we focused on large-scale genetics and neuroimaging analysis, and 2 INRIA teams were involved here. My team focusing on storage and data-related issues, and another team called Parietal, located in Saclay, so closer to the joint lab, focusing on neuroimaging. And of course, we were in close connection with Microsoft, with the Azure teams, and also with people from ATL Europe. So in this project, we have basically 3 kinds of data. genetics data, SNPs, those were presented also yesterday, so it's great the term has already been introduced. We also have a lot of neuroimaging data, so basically brain images, and behavioral data. That's smaller data that basically corresponds to the presence of some brain diseases, for instance. And the goal here is to find correlations between neuroimaging data and genetic data. Previous studies done by experts of the area established some links between the genetics data and the behavior data. That is okay. For some specific genetic configurations, there are higher risks to develop some brain disease, for instance. And the idea here was to start to make correlations between the genetics data and the neuroimaging data, and to use the brain images to predict this kind of risks or the presence of the disease even before the symptoms appear. So that was let's say, the science challenge. So now, concerning the data sizes, there are millions of variables that represent the neuroimaging data, so the voxels that represent the images. There are millions of variables that represent the genetics data too, so the SNPs. There could be hundreds or thousands of subjects to be studied, so that generates a lot of potential correlations to be checked between each individual brain image and all pieces of genetic data. So in order to do this, well, we started in a quite, let's say, simple way. We thought it would be interesting to assess a MapReduce processing approach. Now remember, at that time there was no Hadoop on Azure, so we somehow started from scratch with the basic blob storage abstractions and the web roles and the worker roles. So we basically started to build everything at that level. So there were several challenges for us at the infrastructure level. One of them was related to the high latency when VMs access the public storage. So let's say the simplest solution was to use those roles, to deploy them, and then use public storage and try to have the VMs access the public storage. Well, when you have highly concurrent accesses to shared data, that doesn't work very well. So we had to try to do something better in order to enable some efficient MapReduce processing. So, and even if we do that, well, we know that we had some previous experience with Hadoop, and we realized that it was not really the best we can get. But we said, okay, let's try with that, and we'll see later. And later on, for instance, we had some challenge related to the optimization of the reduce operation, because just the basic way we apply standard MapReduce to this application was not optimal. So what did we achieve on the infrastructure side? Well, we tried to address all these goals. So basically, to address the first challenge, instead of using public storage, so Azure Blobs, for instance, we said, okay, maybe we should better leverage locality. And for every virtual machine, there is a way to leverage the virtual disk attached to it. So basically, that's what we did. We gathered together the virtual disks of the virtual machines into a uniform storage space. So we built the software infrastructure for that. So now the VMs had a kind of distributed file system deployed within the VMs. Now, we wanted a file system that is optimized for concurrent accesses, for heavily concurrent accesses to data. In order to do that, we went together. We didn't just install an existing distributed file system. We worked on our own, and we relied on versioning and high throughput, on versioning techniques to support high throughput under heavy concurrency. And in order to do that, we had done some previous work in the team on a software called Blobseer, which was designed specifically for that purpose. So I will not have the time to develop that. I will just say that it basically combines a series of techniques like distributed metadata, lock-free concurrent writes, thanks to versioning, in order to allow concurrent writes or reads concurrent writes to shared pieces of information. And that's what we try to push on Azure and to build let's say, the Azure version of it, Thomas Blobs. So this is the final result, let's say. So I'm skipping further towards the end of the project. Let's say 3 years old. 3 years later, I didn't mention that the project was finished actually a few months ago. And what we could achieve is actually shown here, is that we could reduce the execution time from the A-Brain application, that is the application that we are targeting in this project for doing the joint genetics and neuroimaging analysis. So we could reduce the time from this level here. That corresponds to what would happen if we used just Azure Blobs to this level here, which corresponds to usage of Thomas Blobs. We could do this, so that's a gain in the order of 45% in time. We also were able to run this across several data centers up to 1,000 cores, and there is a demo available on that. So in order to reach this goal, we had to go step by step, and there are some smaller challenges, let's say, some sub-challenges that we had to address. For instance, first of all, we implemented a naive MapReduce, and then we realized, while doing the performance measurements, that the reduce phase was really not optimal. Actually, there was a bottleneck at the level of the reduce phase, because we needed a single results to gather, and we needed to gather the results from all the mappers in order to produce something that makes sense. So we basically worked on a refined version of MapReduce, which is called Map Iterative Reduce, which allows basically the reduce phase to happen in several stages with intermediate data, and it works as long as you have associative operations. So we could further improve the execution time this way. So in this picture here, you have the time, again, corresponding to the usage of Azure blobs in blue. Then that was in red is what happens when you use Thomas blobs, so we leverage locality. And what we gain further when we use this map iterative reduce approach. So it was worth doing it. We had the time to go further, so the next point was to go beyond the frontiers of a single data center. There is a limit on the number of VMs that we could deploy on a single data center. There is no reason to say it's an arbitrary limit. It is anyway interesting to see what happens if you want to deploy a large number of virtual machines, for instance, by leveraging resources that are available in different data centers. So how to enable scalable MapReduce processing across several data centers? That was one of the challenges. So of course, this corresponds to quite a generic scenario. It's not specific to our applications. Now, the big problem in such a configuration is the latency that you have between the data centers. So the goal is to minimize the transfers across the data centers. And we came up with a solution for that. It's not necessarily the optimal solution. It's something that we started to do and that we will continue to optimize further. Basically, we used Thomas blobs within each data center and public storage for data management across data centers. And this is how we actually could do that, those measurements that I showed before on 1,000 cores, because we needed 3 data centers for that, actually. OK. So now, what you may wonder, what was this useful for? I mean, what happened? What did the application team do for that? So we worked closely, as I said, with another team focusing on neuroimaging and genetics. So basically, they used the infrastructure to run their algorithms to improve them, and they came up with a new algorithm for brain-wide studies. Basically, it's an algorithm that tries to emphasize, to help in detecting those correlations between areas of the brain and genetics data. So this approach is called RPBI. I'm not an expert of the area, so I'm not going to focus on that. But what you've seen in this picture is a comparison between the results obtained using this new approach and the state-of-the-art approach. So you see better highlighted areas here which are more colorful than the ones you can see here. So it's a quality improvement in this detection process. So that was nice. It was obtained on the Azure cloud. We're very happy about it. But maybe one thing you might wonder is what nice science result did we obtain with this? Did this lead to any science discovery? So actually, it did. We had time after this preliminary study to do something else. Rather than just assessing the impact of one specific SNP on the brain, the idea was to study the joint effect of all SNPs on brain variables. And this comes to the notion of heritability. And so a method was developed for that by our partner team. And in the end, we could experiment it with real data from a reference data set, which is called Imagen. It comes from a European project. It's real data obtained based on very high resolution images. And the result that was obtained is it basically claims the heritability of some specific brain activation signals, which are called the stop failure brain activation signals. So these signals were shown more heritable than chance in all the regions, right? So it was an interesting result that we submitted to the Frontiers of Neuroinformatics journal, and it was accepted a few weeks ago, and we are quite happy about this. We think it's quite a representative result for data science. It's probably the kind of thing that we want to show when infrastructure teams work with science teams that don't know how to use the parallel infrastructure, distributed infrastructure. And we succeed in doing that. So we were quite happy about this result. So the application team learned how to use the cloud and learned that it was interesting to, it could be advantageous to not to have to manage the cluster and to buy it and just render the resources. On our side, as infrastructure team, let's say it was interesting to do large-scale experiments on thousands of nodes and multi-site processing, so we could experiment our Blobster software in this new infrastructure and to refine everything. We could run experiments for up to 2 weeks. So it was quite interesting, more than 300,000 hours of computation used, for instance. So if we want to sum up on this project, basically on the infrastructure side, we met this, we achieved these results, so we could scale up until 1,000 cores and cut the execution time up to 20% by up to 50%. And then on the science side, we established this heritability result. Okay, plenty of publications. So I'm going to skip through them. These are the people involved, and I would especially focus the presence of Radu, who is here, who is the PhD student mainly involved in this project. Thanks to him, all this technical work was achieved. So the question is, what's next? Once this was done, as I said a few months ago, we started to think about something else, going beyond what we achieved. For instance, handling more, not only MapReduce workflows, but any kind of workflows. We could see several relevant examples yesterday. And also focus on this multi-site infrastructure and try to better understand what are the challenges related to that. So dealing with workflows, I'm not going to explain that. You already know what it is. Several examples were given. And we will focus on what is difficult in order to enable this kind of workflows on multi-data center clouds, assuming quite natural things, the fact that each cloud has its own data and its own program. Some data shouldn't leave some site. Processing must happen in different places. So it matches well a real situation. So there are several challenges related to that, related to how to efficiently transfer data, how to group dates, tasks and data sets together in a smart way, and how to balance the load. And I'm just going to focus on the first challenge related to data transfer, quite with two examples. For instance, one approach we started to explore is the way to leverage network parallelism by enabling multi-pass transfers between the sites. So basically, it consists in allocating dedicated VMs here just for the transfers. So you rent additional VMs to increase the level of parallelism. We can do even better than that. We can also allocate VMs on separate data centers in order to further increase the level of parallelism. It is, of course, it can increase the parallelism, but of course, obviously, it has some cost. So it is interesting to also assess the trade-offs that might appear, because of course you increase the degree of parallelism, but you pay for that. So the right question here is, how much are you willing to pay to have better performance, and actually how much is it worth paying? Because at some point there is what you get extra is not worth anymore, right? So this kind of challenges are the ones that we are going to focus on in the next project. Streaming was also mentioned in some applications, in some presentations yesterday. So we are going also to look not only at batch transfers, but also streaming in all these multi-site settings. So basically, and this is actually my slide, my last slide. In this project, actually, what we are going to look at several things: how to adapt workflow processing that right now is mainly targeted for single-site cloud infrastructures. Also, we will work also at the expressivity level. So in this second project, our partner team is another team from India called Zenith, who's focusing on scientific data management and more higher level aspects than us. We are at a more system level, let's say. So they are interested in this aspect. We are going to build the cloud data management framework addressing these challenges that I mentioned before, and work also on scheduling issues. And I guess this is it. Thank you.
Thank you. We have time for a question. And Alex?
So so if I launch multiple VMs and I start transferring from all of them, it might be network parallelism, but it might be other kinds of parallelism that you're getting benefits from. Right? Like, is it clear they're all taking different paths, or was it just you hadn't saturated the pipe that you needed? The bottleneck was, I don't know, like the NIC or something. You know, the network interface on the local machine.
So it's like, well, it's like sending data. At some point that might be a limitation related to the one-to-one communication between two VMs situated in two different data centers. By allocating new VMs in the same data center as the sender side, that communication might be very, very fast, actually. And then you can have multiple sources that send to the destination on the receiver side. And that can improve we did experimental studies for that, and we could measure that it was worth doing that.
Yeah.
So your Thomas blobs provide better performance than using like S3 or Azure blobs. Can you briefly say how it would compare to just JBODs on my local, just raw disks using HDFS?
It basically performs better, actually, because prior to these studies, we experimented a Blobsphere framework, which actually implements those principles of leveraging versioning and so on within Hadoop. So basically, we replaced HDFS by a Blobsphere-based version of Hadoop that is optimized for concurrent access. It allows concurrent writes, for instance, and reads concurrent writes with a distributed metadata management scheme. We could, in the initial evaluations, we could get up to 30% improvement just by keeping the standard configurations of Hadoop. So that was kind of starting point for this project. Let's try to see how it works on a real cloud. If I were to start it now, I would probably do things differently because we have Hadoop on Azure, so we would probably explore what would happen in that framework.
Would be interesting. Have you tried comparing Hadoop on Azure with what you've got there?
We haven't tried that, but there are some preliminary experiments that Radu did. I don't know if you want to say a few words about that.
Well, actually, why don't we save that to the break and we can talk about
it.
Okay. Right.
So
Gabriel,
thank you.
Thank you very much.
Thank you.
So I'm going to introduce my colleague, Alex Wade, if I live long enough. I think I will.
Yeah, please do.
And he can go right ahead.
Great, thank you. My name's Alex Wade. I am on the MSR Science Outreach team. And I was going to try to set the record for the fastest talking presentation, but after Roger went yesterday, I decided I couldn't compete with that. I do have a lot of slides, though, so I'm going to be clicking furiously here to get you to the break on time. I want to go back to some of the things that Merce was talking about earlier, and I'm sure everybody pulled out their dog-eared version of the fourth paradigm before they came to this and refreshed. But a lot of the things that we're talking about here with data science and data-intensive research have a lot of implications for the less sexy parts of the care and feeding of the research data themselves, and what are the implications for institutions and for labs and for librarians in taking care of that. Specifically, one of the bits that I think Jim Cray evangelized was this notion of having all aspects of the data available and online. Having the raw data, having the workflows, having the derived and recombined data available to facilitate new discoveries and to facilitate reproducibility. And so Merce didn't mention this, but she was co-author on a publication that just was released in, what was it, PLOS Computational Biology last week, a couple weeks ago, that talked about 10 simple rules for the care and feeding of scientific data. I don't want you to use this as an excuse not to go and read the article. It's an open access article on PLOS, so do that. But the shortcut is these are the 10 simple rules right here. And I want to build on some of the things that Merce was talking about with respect to the tools that Harvard is building out and the Dataverse network. But I want to focus specifically on these 4 right here, about sharing your data online, linking to your data from your publications, publishing the code that goes along with that data, and then fostering and using data repositories here. So, on the first item, repositories, there's a number of different software packages that are available right now for building out a data repository. The general sort of push that's been going on over the past couple of years with efforts like DataCite are to promote the discovery of the data sets as a continuation of the publication. In other words, you publish your research, somebody reads your research, and then they say, I want to go and get to the data. And that's the primary avenue for finding the data, is via the publication, via assigning a DOI to the data set along with the publication itself. But I want to build on that a little bit and talk about what are some next steps that we can take to facilitate the access and reusability of those data sets, and then finish then with a sort of little bit more forward-facing look at how we can simplify the discovery of those. Merce mentioned some work that we did with California Digital Library and building out the Data Up platform, and Chris Toll and Stephen Abrams from CDL are also here if you have any questions at the break about this. But Data Up is intended to be a browser-based open source front end for data repositories that allows individual repositories to plug into that and provides end users an easy way to integrate with our own personal cloud storage. So we plug this into the OneDrive storage, but then to apply a simple set of rules then for describing the metadata around your data sets and having that get published into a data repository. This is available for folks to work with. If we're looking for other people to get involved in building sort of on-ramps between the Data Up software and their repositories. So do talk to us more about that if you're interested. But if you're setting out right now and you're saying, I'm a lab, I'm an institution, and I need to build out a data repository, there's a large spectrum of software that's being developed to do this right now. There's some traditional software packages that have been used mostly for publications, things like DSpace and ePrints, that are either modifying or writing white papers on how to use those repositories to manage a data file, more or less. Dataverse network that Merce talked about. And I'm going to talk briefly about the CKAN software from the Open Knowledge Foundation. This is something that's generally being used in the UK, globally now, a lot of use in sort of the open government data initiative type of use cases. But then there's also hosted repositories, things like Figshare as a software as a service, a place where you can go up and upload your research data into Figshare, get a DOI for that. Microsoft has a service as part of Windows Azure called the Windows Azure Data Market, and I'll talk briefly about that. So really quick, with the CKAN software, I'm going to jump in here and do I'm not going to give you a demo, but if you go to ckan.org, you can walk through this yourself. There's a live demo link right here. And you'd get dropped into a data repository with just a whole bunch of things that people have dropped into it. But the general idea is that you can have a browse and search-based way of drilling down into these data sets here. So you can filter by organization, you can filter by group, you can filter by tags, the actual file format, and the licenses. There's a search engine into it. And if you pick a data set, see if I can find a good one here. Road closures. You get access to the files themselves, but then also the ability to drill into the data, to preview it before you download it. And that's a very intense data set with 2 whole entities in there. But play around with that just so you can sort of see what the CKAN software gives you. If you wanted to create an instance of this is something that's supported right now on Windows Azure. And I'm going to walk through just a lot of screenshots very quickly, just to give you a sense of how quickly this can be done. It actually took me longer to make the screenshots than it took me to create the repository. But the general idea is that I'm going to copy 2 images out of the VM depot into my own blob storage, and then I'm going to create a virtual machine from each one of those disk images, and then I'm going to link them together. Those are the 3 steps. So when you log into Windows Azure, if I go to virtual machines, you can see that I have no virtual machine instances here. And if I click over on the next tab over there, images, I have no images either. So I've got an empty shell here. And this Browse VM Depot is your entry point then into this set of community contributed virtual machine images. So huge number of them. I don't know how many we have these days, but if you browse in there, you can see there's 2 CKAN disk images there. There's one for the CKAN database and one for the CKAN web front end. And I can grab one of those. This is the database. I'm going to tell it which image I want to copy it into, give it a name, and it starts copying. I go back in there and now grab the web, put it in the same region, give it a name, and that starts copying over. So I now have 2 disk images here on my site. I register them, they're available. So now from those images, I can create my virtual machines. I go in, create a virtual machine, come down here to my images. I see the 2 that I just copied over. I give the VM an image, pick a size, and boom, that's starting up now as a VM. Do the same thing with the web. And I've got my 2 VMs now up and running. The last thing I need to do then is go in and link them together. So if the web front end is talking to the database, and I click the link resources, pick the storage account, and now it's up and running, and I have now an empty data repository that I can log into. I can start creating my accounts. I can start populating that. Okay? So that's the model for taking a disk image off of the VM depot and building your own data repository. As Merce said, the Dataverse network is working on this as their 4.0 release comes out in June. This will also be available via VM Depot. So I want to build on that then and talk a little bit more about evolving beyond the notion of a data repository as a place where there's a thing that you're going to go out and get. And one of the nice things that I like about the CKAN repository is that they start to think about the ways that you can now start interacting with this data beyond simply grabbing a CSV file and downloading it. So they have over here this link for the data API. So you can look at the data, you can sample it, you can apply some filters. They even have some graphing and mapping capabilities so that while you're in your browser, you can play around with it and say, is this the data that I want to interact with? And once you say, yeah, this is what I want, rather than downloading the data set, the data API here then gives you how to update it, how to query it, the direct access to the data themselves. So you can write an application that is querying it out of the data repository rather than creating your own instance of that data set. And similarly, the Azure Data Market does this as well. So one of the areas that this becomes particularly important, oops, I'm not going to, in the interest of time here, so I don't feed into your, eat into your break time, is one of the ways that this becomes increasingly important is that when you're dealing with a very large data set, you don't want to download it. So the example that I was going to show here, if you go to the Azure Data Market, is we've taken a large amount of data out of the Microsoft Academic Search service that we've been building up. So you have something on the order of 50 million papers, 20 million authors there, a large number of relationships. You can actually see the individual SQL tables in the model there. And you don't want to download that entire data set if you're interested in dealing with a subset of it. So like the CKAN repository, the Azure Data Market has a RESTful API where you can go in and query that data and either bring down the subset of data that you want to store locally or just have that be the back-end database to the application or the analytics that you want to be doing there. So if you go to the Azure Data Market, you'll see then, just like CKAN, there's a number of different ways that you can browse into the data sets that are available there. You can browse by domain. You can browse on the free ones versus the ones that have a fee associated with them. And somebody asked me yesterday, how can we take our research data and get it into the cloud, but in a way that we don't need to pay for it. And one of the things that the Azure Data Market supports now is a cost recovery model where you can make your data available, and you can make it available charging the consumers of that data only as much as you need to pay for the sort of tenancy bills, the hosting bills, to put that data into Azure. So it's something to consider. It's not quite wide open enough for the world to start coming and putting their data into it. So the Azure team, I think, is really focused on the high-value data sets. And you'll see there's only a couple of hundred data sets in there right now. But that's an approach to think about for a sustainability model. The way, in the case of Azure, that you get your data back out is via the OData protocol. If people aren't familiar with it, go check out odata.org. It's under the umbrella now of Oasis being standardized, but it's builds on top of HTTP and builds on top of REST, and you have the option then of getting the payload back in JSON format or Atom format, and it's a very simple way of interacting with very large data sets. One of the nice things about it, if you're interested in this aspect, is that it's also a read-write protocol. If you have a data site that you want to be writing back into, there are write operations. One of the other rules that was mentioned is publish your code in the article by Merce and Alyssa Goodman and others. This is a project that was just started up by collaboration between Figshare, the Mozilla Science Lab, and GitHub, which makes it really easy to plug your GitHub repository into Figshare. And the general idea is if you want to snapshot your code, get a DOI for your code so that you can say, this is the instance of my software that I use to produce that data set, you can essentially plug in, I think they've got a Firefox plugin, but you can plug in your data repository into Figshare, snapshot it, it will bring all the code over into Figshare and give you back a DOI for that. So it's a really great idea. Kenji was also involved in a workshop, you look startled, at Oxford a couple of weeks ago with the Software Sustainability Institute. Is that who ran it?
It went live yesterday.
Yeah, so a great blog that he just published last night on our Connections blog. Check that out. It talks about software as a part of scientific reproducibility. And the last thing that I'll leave you with, maybe even finish in time for the break, is this notion of moving beyond linking to your data as the sole way of discovering research data. This afternoon, somebody's going to come over and talk about some of the tools that are being built into the current version of current generation of Excel. And I think we had a demo last night out in the lobby. But just sort of thinking forward a little bit on how research data could be as pervasive as web pages on the internet. So I didn't go to the Spitfire Grill last night with the rest of you. I had to go home and pick up my boys, but I got home in time to see the last 10 minutes, I think, of the hockey game where the Flyers killed New York Rangers. And instead of opening up my web browser and looking at the web of web pages, I opened up my data browser, Excel. I don't have any data in Excel right now, but I was interested in learning a little bit more about the Flyers. Haven't really been following them this season. So I clicked online search. I've got a search box over here, and I typed in, can't really read that, Philadelphia Flyers roster. And I got a set of data sets back. So this is Bing indexing data from the web. Most of the results here are actually tables that they've scraped out of Wikipedia, but you'll see other data sets in that set. And imagine that this was scientific data now. I had a need for some data. I typed that need into a search box, just like you would into a web search engine, and you get back a set of data. First one says current roster Philadelphia Flyers. That sounds good to me. And I bring the data into my spreadsheet. And this is where you'll start seeing some new tools this afternoon, but there's a very simple one that Excel 2013 has, which you can just take the data set and you can say, here's some things that are roughly places in the world. Cast those onto a Bing map. And so within about 90 seconds, I went from having an empty Excel spreadsheet to having a map of the birthplaces of all the Philadelphia Flyers. Because I just want to play around with that data. So I just want to leave you with that sort of notion of thinking about data discovery, thinking about research data, getting it in the hands of users for new experiments in sort of this sort of paradigm. I think I'll finish with that right at 10:30, and I'll leave 1 minute for questions.
Oh, amazing. We've got down to 10:30. Questions?
Karen, question?
Yeah. Did I miss something?
All right, I think everybody's ready for a break. The people from this session.
Question, Merce?
I have more question or comment, but I can also discuss it over the break.
Either way, you would.
Why don't we go ahead and take a break?
Yeah.
All right.
Let me thank the panel.